Hi everybody, today we're going to talk about graphing exponential functions. So what makes a function exponential? We've seen different kinds of functions. We've seen linear, quadratic. Earlier in the year we graphed square root function, reciprocal function, absolute value, all kinds of functions. If you remember, if you go back to our unit 1 part B of that. All right, so we're going to graph exponential functions. So what makes a function exponential? Well, the independent variable, which is generally we use x to represent that, is in the exponent. All right, so that's what makes it exponential. That's it. That's the secret. Now, the b I have here, the variable b, is our base. Right now, the trick with exponential functions is the base can be any number. So I'm just going to circle and highlight that there. Okay, so for example, I'll just write a few random ones here at the top. Like we could have y equals 2 to the power of x, or y equals 3 to the power of x. Those are some really common ones. Or y equals, how about 1 over 10 to the power of x, you know? The base could be anything. What could be y equals negative 15 to the power of x. Okay, so the base can be any number. It's just that the x is up in the exponent. Now, the thing about these graphs is they all generally have just like every quadratic we encounter has kind of that same shape, right? A quadratic has that parabola shape. Every linear relationship is a straight line. So these ones also have a common pattern no matter what the base is. And we're going to graph some of those in just a second. Before we move on, though, let's talk about, because this is going to come up a lot over the next couple lessons, is the difference between an increasing function and a decreasing function, okay? So an increasing function represents growth. A decreasing function represents what we call decay. So when we're looking at the b, okay, that tells us whether it's increasing or decreasing. If b is something greater than 1, so for example, if b is 2 or 3 or 4 or 4.5 or, you know, whatever, but a number greater than 1, it's increasing. Now, if b is something in between, and again, ignoring the negative for now, because I put an example up here when I said it's negative. Don't worry about the negative, just think about the absolute value of that number. If the b is something between 0 and 1, so like a half or a third or a quarter, and again, that could also be a decimal number like 0.5 or 0.25. That means we're going to be shrinking or decaying. We call that a decreasing function, okay? All right, so we've got some other definitions here, and you can read about them yourself in the handout, okay? But the big ones we're going to want to talk about at the bottom here are what's called an asymptote. And I'll show you what that looks like when we graph it, okay? An asymptote is a special kind of line, okay? So an asymptote, I want to point that out so that before we get down to graphing, okay? This is basically a line, okay, that your graph gets closer and closer to but never touches. So if you remember back, you might have forgot, but we saw this with our reciprocal function, right? So again, your graph gets closer and closer and closer to this horizontal vertical line. In this case, it's going to be horizontal, okay? But it never touches it. The other important thing we want to know is for all exponential functions, their starting one, before transformations, okay? All of them start with a y-intercept of 1. Now, why is that? Think about, look at these examples at the top. What if we put 0 in for x for all of these, right? What would we get? Well, what's 2 to the power of 0? 1. What's 3 to the power of 0? 1. What's 1 over 10 to the power of 0? 1, right? 1. They're all 1. So in other words, when you make x 0, you always get out 1 for these. Now, this is before we start transforming it. So we're just looking at the kind of basic functions where there's just a base, any base to the power of x, before we get carried away and start doing some transformations. And then we'll see that that y-intercept will shift, okay? But those are the important features that you want to know moving into grade 12 about exponential functions, the main stuff that you kind of want to be able to recall and know about, okay? All right, so let's get into drawing a couple key important functions here. Okay, so these are going to be our two kind of starter functions. I got them both labeled F, which isn't a good idea. So I'm just going to change this guy to G. There we go, G of X. F of X and G of X. So the one has a base of 2, the other has a base of 1/2. So when you get into these graphing questions, the first thing you want to identify is what's your base. It's pretty obvious here, but when we get in the ones that have all the transformations on it, that's where people tend to get lost. So let's just be really clear here what our base is, right? This one has a base of 2, and this one has a base of 1/2. And again, here it's super obvious. Like I said before, you get into transformations, which is going to be the next lesson, and then a lot of us tend to lose sight of what the base is. Okay, so I'm going to make some table values here. I'm going to draw some tables, and let's come up with some points that we can graph. Okay, so I've got some tables set up here for x and y. Let's start out with y or f of x, or y, equals 2 to the power of x. So again, don't forget that y equals f of x. So f of x is, or g of x in this case, y equals g of x when we make our graph, right? The y coordinate is that function, okay? All right, so getting back to this, let's start with this first one here. So I'm going to start in the middle here. Let's start with the easy number, 0. So what's 2 to the power of 0? So what I'm doing each time is I'm replacing the x here, and I'm saying, all right, what's 2 to the power of whatever? In this case, 0, which would be 1. All right, so 0, 1. All right, so actually I'm going to do that in a different color, so when I graph them, I can kind of tell them apart. So this one, let's do this one in blue. 0, 1. All right, so 0 over 1, just like we said. You sub in 0, you get 1. Let's sub in 1, 2, 3. You know, we could keep going. We're going to run out of room, though. But, 4, so on and so forth. All right, so 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. All right, so they're getting bigger and bigger, right? So we're 1 over 2 up. We are 2 over 4 up. There we go. 3 over 8 up. And my next point's going to be off the graph, up here somewhere. But I can't quite fit it in. All right, so if we connect the dots here, here we go. Connect the dots, connect the dots. There we go. Up, 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 up. Not the best. Now, we don't want to cross that line until we get right to that top there, right? Because that 16 it's basically up here somewhere, right? So we don't really want to be crossing over yet. There we go. That'll do on that side. So if you look at that and you think that kind of looks like a half a parabola, it's a little sloppy, but it is. It basically looks exactly the same or almost the same as a parabola, right? You're getting that curve. All right, now what happens when we go into the negatives, like -1, -2, -3, and so on and so forth? Well, I'm going to go a little farther and go, okay, well, what's 2 to the -1, right? 2 to the -1 is 1 over 2, right? 1/2, or 0.5, right? So I'm going to kind of squish that in, 0.5. All right, so we're going to go 1 over to the left and 0.5. We're at 1/2, right? What's 2 to the -2? All right, that's 1 over 4, which is 0.25. So we're getting smaller. So it'll be like this. We're getting really tiny. So if you're thinking, oh, this is going to be kind of tough to graph, you're right. Just do the best you can with these. There's going to be a lot of decimals in these graphs, and we just try to get as close as we can. Okay, so when we start doing some of these, don't panic. Just get as close as you can. 2 to the -3, right? Well, that's 1 over 2 to the 3, right? So that's 1 over 8, which is going to be even smaller, 0.125, right? Now, what happens as we keep going? As we keep going, smaller and smaller and smaller, right? We go -4, -5, -6. The idea is this thing is going to keep getting smaller and smaller and smaller, right? But it's never going to cross 0, right? It's just going to become smaller and smaller and smaller. If you ever heard of something called Zeno's paradox, now, see, it looks like I'm crossing the line. I don't want to be crossing that line. This is sort of an example of that. The idea, it's getting smaller and smaller and smaller, but it never actually crosses 0, right? It'll become a tiny, tiny decimal. So, for example, like if I made the x instead of like -3, what if I made it like -1,000 or something, or 100, right? If you go way over here, you go, okay, well, what's 2 to the -100, right? You're going to get a tiny decimal number. Let me just bring my calculator up, right? And if we go, all right, what is 2 to the power of 100, and I make it negative, right? It's written in scientific notation, so it looks like it's 7 point something, but it's actually 31 zeros and then a 7, so it's like 0.00000, right? It keeps going, 31 zeros, and then it's, 788, right? So it's a really tiny number, but it's not 0, and it's not negative. It's never going to be negative. It's just going to get infinitely smaller. It approaches 0 is what we say. It approaches it forever. Right? It gets tinier and tinier and tinier. Now, this isn't so much a real world concept as more of like a theoretical concept, right? The idea that the number gets tinier and tinier and tinier and tinier. So the line that it's getting closer to is called the asymptote, and I'm going to draw that in. So our asymptote, which is kind of an odd word, right? Okay, in this case is y equals 0. It's this horizontal line here. Now, for this, it's just going to be our x-axis, right? When we do transformations, it might move. So when we get into transformations in the next lesson, we got to be, the most important thing to do is to graph where that's at. So in this case, I'm just going to label it right here at y equals 0. So that's the line that our graph gets closer and closer and closer to, but never ever touches. Okay, I'm gonna label that. There's my asymptote. All right. Okay, so there's the graph of y equals 2 to the power of x, or f of x. If we want, since it's over there, that's the nice thing about f of x and g of x and labeling it with function notations. You could just label it like that and then look over here and there it is, right? Okay, let's do the other one here. Let's do 1/2. Now, the thing is, once we graph this, you might notice it's going to look exactly the same. I shouldn't say exactly, but it's going to have the same shape, but flipped. So let me show you what I mean. Let's start with 0. So what's 1/2 to the power of 0, right? Let me kind of write all these in here. I know it's going to get a little squishy, but 1/2 to the power of 0. Well, that's 1, right? So 0 over 1 up. There's that y-intercept again. They share the same y-intercept. Well, what if I make it 1, 2, 3, right? Keep going. Well, what's 1/2 to the power of 1? That's 1/2, right? Which is 0.5. Okay, so it's right here. What if I go so on and so forth? 1/2 to the power of 2, okay, which is 1/4, which is 0.25. Which is right here. And then so on and so forth. 1/2 to the power of 3. Well, that's 1 over 2 to the 3, which is 1 over 8, which is 0.125. So again, it gets smaller and smaller and smaller. It's just going to get closer and closer. And it gets so small that it's almost impossible to draw these points other than just to put them right against that line. So when you do it, just basically draw your graph like it's not supposed to be touching this line, but it gets so close that it appears to be touching, right? So as long as we're not crossing that x-axis, we're okay. Now, on the other side, what if we make it -1? Well, what's 1/2 to the -1? Remember, that negative fraction causes a reciprocal. So this would flip it and make it 2 to the 1, which is just 2. So here. And so on and so forth. What if I make it -2? 1/2 to the -2. Well, flip it, because it's negative, and it becomes 2 to the 2, which is 4, right? And so on and so forth. So it's getting bigger on the other side. And then, to the -3, well, that's 1/2 to the -3, which is you flip it, so it's 2 to the 3, so it's 8, and so on and so forth. So it gets bigger on this side, right? As we're going in reverse, basically. All right, let me just try and draw this the best I can here. And the next one would be 16, right? But that's going to be way up here. All right, that's not perfect, but that's going to have to do for now. And there's g of x. All right, so what are the differences? Well, this one is a decreasing function. Why? We read a graph right from left to right. So as we move in this direction, right, we're moving forward. The purple graph, the 1/2 to the power of x, is decreasing. The first one I drew is an increasing graph. Okay, so we call that exponential growth is what this one, the increasing one's called, and the other one's called exponential decay. So this one's called growth, and this one's called decay. Okay, it's another word for increasing and decreasing. So when you see those words pop up, that's all they mean. What else can we say? They both share in common some certain features. They both have, their domains are the same. Both of their domains are x can be any number. You can put anything you want in for x. There's nothing stopping us. Remember, when did we have domains that weren't x can be anything? Things like when x was underneath a radical, right? We can't have negatives, so that's a problem. When x is on the bottom of a fraction, that's when x can't be 0. So those are the scenarios where our domain can't be anything, right? Now look at our range. They both start, it's going to change as we do transformations later, but our range is going to be, oops, I'm writing those too fancy. Y is greater than or 0. I was going to say equal to, but y is never 0, right? Remember the y coordinates get smaller and smaller and smaller as it gets closer, but they're never 0. We already said what the asymptote is. That's a really important feature, especially when we get into transformations. And you know what? That's about it. And the other important thing to keep in mind, like we mentioned earlier, is the y-intercept for both of them is 0, 1, right, to start. So that's any of our exponential parent functions. What do we mean by a parent function or a base function? Okay, that's our starting ones with no transformation. We just have one base to the power of x, 1/2 to the power of x. That's like as simple as they get, right? Make the base whatever number you want, and there you go. All right, so what you're going to be doing for the first bit of work is you're going to be graphing a couple yourself. And what I want you to do is just basically do what I did, just plug numbers in. So I'm going to give you a couple to graph, some pretty basic ones. I think one of them is going to be 3 to the power of x and 1/3 to the power of x. So again, those are going to be the same thing but flipped around. Of course, you're going to get some tiny decimal numbers, but don't panic. Just graph them the closest you can, like I did here. The idea is to get that general shape, and the shape's going to look pretty much the same, okay? It just might be stretched out a little bit or compressed a little bit, as you'll see. Before I move on, I just realized, looking at my notes, I forgot to talk about something on the previous page here. So I'm just going to go back and just really quickly talk about one thing. Just coming back here, I want to zoom in and just talk about this part right here, this exponential pattern. I forgot to talk about that. It's an important, simple but important little feature. So I'm going to cut that out and we're going to talk about that right now. Okay, so what makes a pattern an exponential pattern? When you're looking at a table of data, this is something simple, but we have to know it. Again, first you got to check, are the changes in x consistent? We got to make sure our x coordinates are in order, right? Because if they're all jumbled up, then we can't tell if there's a pattern. So in this case, yes, I'm going up by 1 each time. So if your x coordinates aren't in a pattern, right, increasing or decreasing by something consistently, you got to rearrange them. Or if it's skipping numbers, you can't tell. So that's the first thing. Is this in order? Yes. Is it a constant pattern? We're adding or subtracting by something, right? And we wanted a pattern where we're adding or subtracting, okay? Now, on the other side, what's the change in y, right? Let's go through our different patterns. So what are we adding or subtracting by here? Well, we're clearly adding. So 0.5 plus 0.5 is 1. 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4 is 8. I think I've picked one that's a little too simple to spot the pattern in here. So when you're doing some of the homework, this one, it's my fault. I made this one too. You can tell right off the bat. Obviously, I'll show you why, but maybe just looking at the numbers we just did, why this is exponential. It's not always so easy. This is too easy of a parent function, but I'll show you the method. The method's the same. So now, remember, how do we know if it's linear? It's linear if the first differences are consistent, right? So the change in y are consistent, right? In this case, they are not, right? So if I was adding by the same thing, that would be linear. Now, how do we tell if it's quadratic? Remember, if it's quadratic, if the second differences are constant, right? So what am I adding by here? I'm adding by 0.5, I'm adding 1, I'm adding 2, right? So in this case, it's not quadratic, right? If you're adding or subtracting by a constant second difference, it would be quadratic, right? So what does linear mean, right? Linear is a straight line, right? What does quadratic mean? You get that parabola shape, right? So it's neither of these. It's exponential if the second differences, so this is where it's key. When you check the second differences, okay? Now again, you can spot it right from the table in this case. So don't assume they're all gonna be this easy. They are not. If the second differences are multiplying or dividing by what we call a common ratio, okay? So if the second differences are a common ratio. So what am I multiplying by here each time? I'm multiplying by 0.5 times 2. 1 times 2. 2, right? So now you can already spot that pattern from the initial points. Again, that's my fault. I wasn't thinking when I picked these points. I made it too easy. Okay, so let's write this down here. This is important. If the second differences, I'm gonna write down here. There we go. So if the second differences are a common ratio, it's exponential. So when you do the homework, check it by showing me that you found the second differences, that you're showing this. And then I'm gonna basically say, what is the common ratio? So maybe you're multiplying by 2. Or you could be multiplying by a half, right? Which is the same as dividing by 2, right? Something like that, okay? Or maybe you're multiplying by 3, right? Or maybe you're multiplying by a third, which is, again, the same as dividing by 3. So basically multiplying or dividing, right? Where linear and quadratic are found by adding and subtracting, okay? So there's a few questions you got to do really quick. Just show next to the tables, basically show what I showed here, and then state what the common ratio is, right? And if it's linear or quadratic or exponential. All right, so that's the end of this lesson. Check out the next one where we're gonna get into actually doing transformations. Now, before you learn to do transformations, you really gotta get used to graphing the basics again first. So make sure you know how to graph these, right? We're gonna start with these tables here, okay? We're not gonna use quite as many points, but that's what we're gonna start with when we graph these, okay?